Now, what is it that distinguishes the general purpose computer from a embedded system? If you look at an embedded system, let's say like a calculator or maybe washing machine or TV or refrigerator, they all have computers inside them, right? Small microprocessors. Now these microprocessors are already hardwired and they cannot perform everything that you need. They are programmed in such a way that they can do only specific tasks on pushing a button. Now the main difference between those computers and the general purpose computer is the programmable way. Users can change the program, and then by changing the program we'll be able to accomplish different things using the same machine. Got it? So the main difference between other computers and the general purpose computer is the programmable memory, or there is the memory in which we are going to store the program, and by changing the program we'll change everything, right? It is also sometimes called as stored program architecture. So now we are going to discuss about the general purpose computer. We should be able to perform anything that we like, that should be computable. If something is not computable, even computers will not be able to do that. Okay, let us say something is computable, then you should be able to program it. Got it? So what are the main elements that we need? In the previous session we have seen about the instructions that are required, and now we are looking at how to implement these instructions, or how to implement at least some of these instructions. So if you look at a computer, what are the main parts that you need? So if you are looking at the parts, the first main part that comes to my mind is memory, right? You can think about it. You can think about all the possible things required in order to build a computer. So the first thing that comes to my mind is memory. So why is memory required? It is definitely required in order to store the program, and now in that program our CPU has to execute line by line, isn't it? And then when we want to change the program, we should be able to change it. For that reason we need the memory, right? Memory is going to take a new program and it is going to execute it. After its execution we are going to take the next new program, correct? So first thing is we need the memory. Okay, and now what does the program contain? Mainly it contains instructions to perform arithmetic actions or logical actions or shift operations. Therefore we need a circuit or the hardware which should be able to perform arithmetic and logical operations, right? So let's call it as ALU, arithmetic and logical unit, right? So what do I mean by this? We should be able to have this circuit which should be able to perform addition, right, subtraction, multiplication, division, maybe ANDing, ORing, right, exclusive OR, masking, so everything. So there are lot of instructions, and all these instructions are supposed to be performed by this arithmetic and logic unit. And how to design this? About the memory we have already discussed in digital. What is a memory and how to design it, and the decoder and the RAM matrix, everything we discussed it when we talked about this in the digital topic. You please go to digital and then see about this. And then coming to this arithmetic and logic unit, there we have discussed about the adder. Using the adder we are going to perform even subtraction also, and using the adder and subtractor you can perform multiplication and division, right? And also we have discussed about the circuits which are required to do ANDing, ORing, exclusive OR, all these operations. So how to build this, we know them, right? So how is ALU designed? We know it internally. How is it organized? We know it. It is going to contain the circuits which are nothing but the combinational circuits. We have already seen it. Now what are the other things that we need? If you have ALU and memory, is it enough that we can just execute the instructions? It is difficult. The reason is these circuits, this hardware is faster and memory is slow. So we need, because memory is actually very huge, and so getting into the memory and getting some data is going to take time, and our ALU is actually faster. So what we need is some type of memory which is smaller and which is faster, or at least the speed should match at least with the ALU. If it is not faster than ALU, at least you should come up to the speeds of the ALU. Got it? So for that reason, we are going to have a smaller memory units which are called as registers, right? And what is a register? A register is a collection of bits, and every bit is stored in a flip-flop. Therefore you can think of register as nothing but a sequence of bits, or which is nothing but a sequence of flip-flops. So the way the flip-flops are going to be connected, or the circuit is going to be designed, we have already discussed about the flip-flops in digital. You please watch that topic. Either a flip-flop here can be JK flip-flop or D flip-flop, both are used in general. Okay, now what are the various other things we can perform by putting all these flip-flops together? Is one thing is, if you are going to put 8 flip-flops together, we can use it as if it is a 8-bit register. Fine. And along with that, we can parallelly load them or parallelly read them. So we can do parallel input, parallel output. I have shown you in digital. And similarly, we can shift them, shift right or shift left. Right, it is just nothing but shifting the bits from one flip-flop to the next flip-flop. We have already seen this, right? And also along with that, we can use these flip-flops in such a way that they are going to act as binary counters. Now what is the advantage of it? By connecting them in such a way that even they are going to act as a binary counter, as a shift register, as well as let's say parallel load and parallel read. So by doing all this, we can use a resistor for parallel loading and then reading parallelly from all the bits at the same time, as well as for shift operations. If you are going to implement that shift resistor circuit using these flip-flops, then we can use it for shift operations. And now if you can implement even the binary counting, then we can go for incrementation without going to the ALU. For example, if you have a resistor R1, and now if you want to write R1 plus 1, which means whatever is present in R1, if you want to increment it by 1 and store it back in R1, you need not go to ALU. You can directly perform on the resistor itself if you have connected it as if it is a binary counter. I hope you remember what a binary counter is, right? With every clock, the number which is stored is going to be incremented. Let us say the number stored is 10, right? If you change this collection of flip-flops into that mode, and if you call that operation, right, if you just trigger the required circuits inside these flip-flops, then the number will be incremented automatically. Therefore, if you look at a resistor, you can perform one thing is load, other thing is increment, and other thing is clear. All these inputs can be performed. If you can connect it in a right manner, you can use it for all these purposes. Got it? So you can load all the bits. How? You can connect each bit to the bus, each flip-flop to the bus, and then to each individual flip-flop you can apply that load signal, right? And similarly, increment is nothing but connect all the flip-flops as if they are a binary counter, and then just pass a clock through them, right? And you enable that increment, then it will get incremented, right? So once you get all these flip-flops into that particular mode in which it is going to act as binary counter, it is going to be useful for incrementation as well. What about clear? For all the inputs you pass 0 and then you give load, therefore it is going to be cleared. Got it? So all these three can be done on the register. Fine. Now these are the very important things, right? So we have memory, we have ALU, and we have registers. And what else can you think of? What do I need in order to execute the instructions? Now if you look at the instructions, we have a sequence in which the instructions have to be executed. First instruction 1, instruction 2, instruction 3, so on. Unless there is a branch statement, you have to execute all the instructions in a sequential manner. Got it? One after the other. And moreover, while you execute an instruction, it is not just execution. There are various phases in the instruction cycle. right? So we have to fetch the instruction, and after fetching we have to decode it, and after decoding we have to execute it, right, in the simplest way. Now you cannot decode it before you fetch, or you cannot execute it before you decode. Therefore these three operations have to be done in a timely manner, which means there should be a timing circuit which has to time all these operations. For that reason we should have some timing circuit, right, which should be able to generate the signals specifying that this is time t0, this is time t1, this is time t2, right? Then only we can perform certain operations. So we need the timing so that we can execute the instructions one after the other, right? And then we need even someone who can actually monitor or control or coordinate the information flow. For that we need control signals. Therefore we need timing signals as well as control signals. We need these two, right? So, and along with them we even need something called as flags. So what are flags? Flags are nothing but a 1-bit information, which is nothing but a flip-flop. Again, flags are also flip-flops. So what can we do on flip-flop? We can set or we can clear. Got it? So these are all the main parts, essential parts we have. And in order to do the execution we need the timing signals, and now we need the control signals to coordinate the information flow between them, right? So before I talk about the information flow, we might require something else. Just think about it. Is there something missing there? We have memory, we have ALU, we have flags, we have registers. Now all of them have to communicate, right? So how are you going to connect them, isn't it? So the connection problem is again there. So how are we going to connect them? You can think of various ways. You can think of a mesh, which means if you have 4 parts, let us say this is one part, this is second part, this is third part and fourth part. If you want to make all of them communicate, then you might think of the simplest organization where you connect every 2 parts together, which means this, right? So how many connections do you need? Here in this case we need 4 C2 connections, right, or 6 connections, right? Now if you have, let's say, 16 registers and then 1 ALU and then 1 memory unit, and let's say 1 program status word, which is nothing but collection of all the flags. Now if you have 1 2 3 4 16 plus 17 18 19, and let us say we have one more, some other part, 20 parts we have. If you have to connect all these 20 units, then if you are going to connect them individually, like if you are going to connect every 2 parts or every 2 units in a kind of mesh, then you have to go with 20 C2 lines, right? 20 C2 is nearly how much? I think 190, right? So 190 lines you need, but then it is going to be really a headache if you have to manage all these wires together, right? That is why the other solution is just have a common bus. So what is a common bus? We have already seen it, right? So common bus is a common channel running to which we connect everything, right? Now what is the disadvantage of this type of bus? At any time only 2 parts can coordinate. Now there has to be someone who has to monitor their activities. See, if you are going to have a point-to-point connection, then you need not monitor, you need not worry about who is using the channel. There need not be any monitoring, because if 2 parts are, if you are transferring data from here to here, at the same time they too can also transfer. But in this case, if you are connecting it using a bus just to reduce the complexity, the problem is if these two are transferring some bits, at the same time some other 2 parts cannot coordinate or they cannot communicate. Therefore there has to be a leader who has to control the information flow between them. For that reason we need someone to produce the control signals. Now why are these control signals required? Mainly these control signals are required to um, give the inputs to registers, right? So to all the parts basically. So these control signals are required to select the registers, right? Either for reading or for writing. We have to select the registers. Also we have to select and enable certain circuits in ALU. For example, if you want to add two numbers, then you have to enable the adder. Got it? And similarly, you might have to read something from the memory or write something onto the memory. Got it? For that also we have to send the signals, one for read and other for write. And we need control signals to set or reset the flags. So for all these activities we need someone to produce the control signals. And now these two things are mainly taken care by the hardware, and the part of the hardware which will be responsible for these two things, it is generally called as control unit. Got it? The part of the part where instructions and data are stored is called as memory, and for temporary purpose we are going to have registers, right? It is also a form of memory. And then flags are nothing but simply flip-flops, and ALU is the part of the hardware which is going to perform the arithmetic and logic operations. And we have seen all of them, like comparators we have seen in digital, adder we have seen it, and we have implemented a subtractor for that. And similarly you can use the adder and you can create a multiplier also. Similarly you can create a divisor, right? So like that, all the hardware which is doing such activities will be present in this circuit which is called as ALU. So we have one unit called as ALU and other unit called as control unit, and the other one is memory, and we have registers, right? And we have a common bus which is connecting all of them, right? And now who will decide what has to be pushed onto the bus and who has to read it from the bus? Again the control unit, right? Using the timing and control signals. Got it? So how to use all of them? So how are all these designed? How are they made is, you can just think of it this way. We'll again get into details one more time, but here I'll just give you a brief overview. So flags are nothing but flip-flops. Memory we have seen it, and ALU we have seen it. Using the logic gates we are going to design the adder, comparator, subtractor, all this. And registers is nothing but sequence of flip-flops. And timing signals, for this timing signals mainly we use that sequence counter. Okay, so what is the sequence counter is, again we have discussed this in digital, right? So the sequence counter is going to give us outputs like it, you can assume that it is a 3-bit sequence counter. Then it is going to be from 000 to 111, which means from 0 to 7 it is going to generate all the numbers. Then you can use 0 as time 0, and then time 1, time 2, time 3, time 4, so on, time 7, and after it is over again we go to the T0. So these will be used for one instruction, and then the next sequence will be used for the next instruction. If one instruction needs only, let us say, 4 time cycles, then after it finishes its execution, the first instruction, it is supposed to clear these to all zeros so that the next instruction will start at time 0. Got it? So we'll have a sequence counter for implementing this timing signal. And what about this control signal? Again we'll use the logic gates to design these control signals. Okay, and what about this bus? So the bus can be designed using a multiplexer. So what I'll do is I'll explain you clearly how multiplexers can be used. And what is a multiplexer? We have already discussed it in digital. You please watch it there. And I'm going to use multiplexer as a building block for a bus. So how a bus is implemented using multiplexer, we shall see it now clearly. After that again we'll put everything together and we'll explain. Okay, fine.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%. And IITs, universities better than IITs, they have very good acceptance rate like 30%, 40. But all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.